Now, let's consider the more complicated situation when the boat has rotated to one side, to an angle of theta. The shape of the boat has not changed, and so the position of the center of gravity is the same as when the boat was flat. We also know that the force of gravity always points down. Note, however, that the shape of the submerged region of the boat has now changed, because some of the right side of the boat has entered the water, while some of the left side of the boat has left the water. Since the center of buoyancy is located at the centroid of the submerged region of the boat, it will shift to the right from its previous position that was here, and will now be located somewhere over here. Archimedes' principle tells us that the force of buoyancy always points straight up. Now, even though the boat is rotated, the magnitudes of the force of gravity and the force of buoyancy are still equal. This is because the boat will always adjust its vertical position in the water until it is in vertical equilibrium and the net force is zero. However, the forces of gravity and buoyancy are no longer aligned, and therefore they generate a lever, which in this case, the way I've drawn the picture, acts to rotate the boat back towards its equilibrium position. From physics, we know that the torque produced by two equal and opposite forces is given by the following expression. It's given by the magnitude of the two forces times the perpendicular distance between them. This perpendicular distance is called the lever, which I will label by L. In the way I've drawn this picture, we should also include a negative sign, because in this picture, the torque is acting in the opposite direction of the rotation angle. Now, the force of gravity is just the weight of the boat. But how do we figure out what the lever is? Well, this is just a problem in geometry. It turns out that the lever depends on three parameters that affect the boat's shape. It depends on the submerged area of the boat, which I'll label by A. It depends on the width of the boat at the waterline, which I'll label by B. And it depends on the distance between the center of gravity and the center of buoyancy, which I'll label by D. To write all of these variables down again, we have that W is the weight of the boat, A is the submerged area of the boat, B is the width of the boat at the waterline, and we call it B because it's typically called the beam in the boat industry. And D is the distance between the center of gravity and the center of buoyancy when the boat is sitting flat in the water at theta equals 0. It turns out that if you work it out, L is given by the following expression, which is accurate for small rotation angles. We have that L is approximately B cubed over 12A minus D times theta. And again, this is only valid for small rotation angles. We now have an expression for the torque as a function of theta, which is torque as a function of theta is approximately minus the weight of the boat, which is just the magnitude of the force of gravity, times this lever, which is B cubed over 12A minus D times theta. And remember that this is only valid for small rotation angles.